over here. Okay, so let's just start with talking about what Gibbs free energy is. So we've been learning about enthalpy, entropy, and we've said that enthalpy, delta H, let's review that. Delta H, if it is negative, is favorable. And delta S, which is entropy, is favorable when it's positive. Okay. Now, we can have different combinations. We can have a negative delta H and a positive delta S, and then that would be always favorable. But sometimes you might have a negative delta H and a negative delta S, right? And that, is conditionally favorable, right? All right. Or you might have vice versa, different combinations of positives and negatives. Now, how can we figure out if overall it's favorable? That's where Gibbs free energy comes in. And what's the symbol for Gibbs free energy? Delta G, yes. Okay, so delta G naught of the reaction. Now there's a formula for delta G. There's actually two. So, let's write this stuff first. Delta, in case you missed the notes, delta G is Gibbs free energy. It tells you the thermodynamic favorability of a process. If it's negative, I wrote it opposite. If it's positive, it's unfavorable. If it's negative, it's favorable. So it's like delta H. Delta S is the opposite one. Okay. There are a couple of ways that we can calculate delta G, and so then there's two formulas that we'll be using regularly in this unit. Delta G, there's actually a little bit more than that, but for right now, we're using this delta G, and this is the naught, right, because it's at standard conditions, is equal to delta H minus T times delta S. Okay, so Gibbs free energy is equal to enthalpy minus the temperature times the entropy. Now, so things to keep track of. This is important. Delta H is almost always given to you in kilojoules, and delta S is almost always given to you in joules. So you have to put them both into the same unit. Okay? So be aware of that. Otherwise, you'll get very wrong answers. So that's one way we might calculate delta G. Or if we're given the Gibbs free energy of formation for the products and the reactants, right? If you're given a chart of those, then you can use that kind of standard formula that we've been using for delta H, delta, and delta S. But delta G can be calculated the same way, the sum of the products minus the sum of the reactants. Okay? So two ways that you're going to see to calculate that in this section. All right. Given the following reaction at 298 K, we have this reaction. Delta H is negative 24.1, and delta S is also negative. Which one of those is favorable? Delta H is favorable, which means this one is unfavorable, right? Now, we have to see what drives the reaction. Is the delta H enough to drive the reaction to be spontaneous? So let's take a look. It's saying, is this reaction thermodynamically favorable? Meaning, is delta G negative? Okay. If so, is the reaction driven by enthalpy, entropy, or both? Well, I can tell you right now that it's not being driven by entropy because this is unfavorable. Okay? So if it is a favorable reaction, this has to be what's driving it. So let's take a look. I made a little note here. This is in joules, so always divide it by 1,000 to get it to kilojoules. We're using our formula, delta G equals delta H minus T times delta S. So negative 24.1 minus all of this multiplied. Don't forget that's negative, and it's divided. Okay. And so I got, and you can all check my math here because I can make mistakes, delta G is negative 22.8 kilojoules per mole. It's negative, so it's favorable. And again, the entropy is not favorable, so this reaction is driven to occur by the enthalpy of the reaction. Okay? All right, does that make sense when I use that term driven by? I mean, like, that's what's like making it happen. Okay, the entropy part is preventing it from happening, so the enthalpy part has to be great enough to overcome that entropy, that unfavorable entropy. Questions?
Sorry, what's the unit for Gibbs free energy?
For Gibbs free energy is kilojoules, well, per mole. And I could even say of the reaction, because this is for the entire reaction, not for one substance.
So where does the Kelvin drop out?
Kelvin drops out. Oh, here. I left that out. So the unit for delta S, thanks for picking that out. The unit for delta S is kilojoules, or I'm sorry, joules per, here's the Kelvin right here. I just didn't write it. So, my bad. I should have. All right. Okay. Other questions about that? Good question. Again, using those units to drive your process, right? Your math process. All right, let's try another one. When calcium chloride is added to water at 298 K, it dissolves and the temperature of the water increases. All right, so here's a big clue. Water is increasing. What kind of reaction is this? Endothermic or exothermic? The water around the chemical is increasing, so it's exothermic. Okay, if it's exothermic, what do we know about delta H?
Negative.
Delta H is negative. So is that favorable or unfavorable? Favorable. Good. All right. First thing they want us to do is to write the net ionic equation. Let me scoot this up a little bit. So we have a solid being added to water and dissolving. So solid, I just put the water up here because I'm not really including that in the equation, but you have to have it to make it work. And then the calcium and the chlorine ions are dissolving and they are dissociating. And then because it's negative delta H, I put plus heat here just for fun. All right. What do you think about delta S for this? What's happening with delta S?
It's positive.
It's positive, yeah. Entropy is increasing, so this would be positive. And that's favorable or unfavorable?
Favorable.
Favorable, good. Yeah, we're going from a solid, a single piece of the solid, to 3 pieces of ions that are free to move. Lots of degrees of freedom there. Okay, predict the sign for delta H. We already did that. Delta H is negative because heat is released into the water. Or we know that it's negative because heat is released into the water. Okay, predict the sign for delta S. And we did that also. Delta S is positive. We know this because enthalpy increases when a solid dissociates and dissolves. Okay, let me scoot this up a little bit. Okay, now we can predict the sign for delta G. And so we can justify, so figure this out. Remember that the formula for delta G is equal to delta H minus T times delta S. Okay, and so we know that this piece is negative, and we know that this piece is positive. So when you take a negative number and subtract a positive number, what kind of number do you get? Wait, what? You take a negative. Let's do an example. Negative 5 minus positive 3. What do you get? Negative 8. It gets more negative, doesn't it? Okay. So no matter what combination, let's do negative 5 minus positive, let's do a bigger number. What do you get? Oh, sorry. Negative 12, right? It becomes even more negative. Okay. So when we have this combination of a negative delta H and a positive delta S, what are we always going to get? A negative delta G, right? All right, so that tells us our delta G is going to be favorable. So this combination is always favorable. Can we talk about the other combinations? All right, flip onto the back of your paper once you have that written down, and we're going to make a little chart. I see people still writing, so I'll wait a minute. And we're going to use simple numbers to figure it out. Okay, let me actually do this on a separate piece so we can kind of work through it together. All right, so we've got delta H, delta S, and delta G. So we just did the situation, not that situation. We did the situation where delta H was negative, which we know is favorable, and delta S, thank you. Oh, here. I don't know if you've got one back there. Delta S was positive, which is also favorable, and when both of those are favorable, delta G is always favorable. And we're going to indicate at all temperatures because that's going to be something that we have to think about for some of the other situations. Now, what if delta H is positive and delta S is positive? What if they're both positive? What do we know about delta H? Favorable or unfavorable? Unfavorable, right? And delta S is still favorable. So let's see what sorts of conditions that would work in. Let's look back at our formula. So I'm going to leave some space. Okay. So if we have a positive 5 minus a positive, let's make a smaller number, 4, what do we get? Positive 1. Is that favorable or unfavorable? Unfavorable. Okay. And our T delta S part was low, right? So let's say that's at a low temperature. What if you've got positive 5, so this is our delta H, let me be specific here, minus positive, and let's go with a bigger number, minus positive 6. What do you get? Negative 1. And this is favorable, right? So if delta S doesn't change, then T could change, right? And if T is large, that would make this part of the formula large. So this would happen at high temperatures. All right, so let's write that up here. So this is positive at low temperatures, meaning it's unfavorable, and it's negative at high temperatures, meaning it's favorable. All right, does everybody see how that works? All right, and if you forget this, the reason I'm doing this with really easy numbers is because you can always do this with really easy numbers if you forget. All right, and it can help you think about it. All right, let's look at another situation where we have a positive delta H, and I'm just using the same numbers. We're going to use 5. And we're going to have a negative delta S. Positive 1. Favorable or unfavorable? For delta G, right? Delta G needs to be negative, so this is unfavorable. Oh yeah, this equals 9. This is really unfavorable. Right? Okay, what if you have a higher number? What happens? Positive 11, even more unfavorable, right? So this is unfavorable at low temperatures, and it's unfavorable at high temperatures. So that means it's always unfavorable. So when you have this combination of an unfavorable delta H and an unfavorable delta S, it just isn't going to, it's not going to be spontaneous. So let's write that up here. So a positive delta H, which is unfavorable, and a negative delta S, which is also unfavorable. And this is going to be positive at all temps. So always unfavorable. So let's see, we did negative, positive, 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 negative. All right, we need to do both negatives now. So negative delta H, which is favorable, and a negative delta S, which is unfavorable. Any guesses? Will this be favorable or unfavorable or situational? It's going to be situational. So let's take a look. Let's pretend our delta H is 5, and let's start with a, we have a negative, let's start with a low temperature. What happens? What kind of number do we get? 9. I think I need to do a better example. So this is positive 9, which is unfavorable. Wait a minute, what did I do? I think, pardon me? They're both negative, so positive, positive. So it's going to be unfavorable at high temperatures, but at really, really low. This is, so, oh, you're right. Thank you. I'm sorry. This is what, yeah, I messed that up. So at low temperatures, that's where I'm like, this isn't working the way it's supposed to be. All right. At low temperatures, it's favorable, right? Needed a better setup there. At high temperatures, it would be unfavorable. Okay, does that make sense? I'm sorry. Thank you for catching that. All right, so negative, the higher this enthalpy is, the less spontaneous it will be. So let's go ahead and write that in. This is going to be negative at low temps. Oh, yeah. Here we go. And positive, which is favorable. And positive at high temps, which is unfavorable. I think your notes have a chart like that too. Okay, but I think it's helpful to go over that so you can think it through, because it's hard to memorize all these situations until you kind of like deeply understand it. And so being able to work it through like simple numbers like this, I think is helpful if you're in like a moment where you have to think about it really quickly. Okay. All right. Any questions for me? What time is it? We have a little bit over 15 minutes, so you can go ahead and get started with this. We will have time. So you're going to finish this, not finish this, you're going to work on this worksheet. You do not need to get it done today. I will give some time on Friday, but we're also going to do 9.4, right? You're going to watch the rest of 9.3, it's 9.3b and 9.4 videos. I'll just make sure they're published before we leave. So that's what I need you to do before Friday, all right? I know a lot of you have some testing and things going on, so I'm going to leave time in class for this. It's not too much, so you might actually get close to done today anyway, okay? Maybe not, but you'll have a head start. All right, any questions before I stop recording? Good to go? All right,